So for those of you here in the room and online, our guest lecturer tonight is LPL Associate Professor Dr. Jeff Andrews-Hanna. And Jeff received his PhD from the University of Washington, St. Louis, back in 2006, working on research on Mars. He later did a postdoc at MIT and became a professor at the Colorado School of Mines. He came and joined us at LPL in 2017. His research focuses on studying the solid planets and moons of the solar system, understanding the tectonics and what's going on inside the planets, using the study of gravity and topography. So, as we'll be hearing about, he was a guest scientist on the Grail mission, which was a mission to study the gravity of the moon, and is also a co-investigator on the Veritas Venus mission, which is going to be a major NASA mission going to explore Venus in the next decade. He's published over 60 papers on the moon, Mars, Venus, and Pluto, and I will turn it over to him. I will say briefly, I forgot to say for any of the students here, that if you're here for extra credit on the way out after the lecture, you can get a stamp, and we're going to have a few giveaways after his lecture. But with all of that introduction, I'll turn it over to Jeff. So
all
go
right.
ahead.
Thanks very much, Mark. So you probably haven't heard that NASA is building a time machine. Not a real time machine exactly. This is NASA we're talking about, not SpaceX, but a time machine of sorts. NASA's going back to the moon with Artemis. Why am I calling Artemis a time machine? Well, Artemis is going to go back to explore the earliest evolution of the moon in a way that's never been done before. So sometime after September 2026, Artemis is going to return to the moon, bringing 4 astronauts, 2 astronauts down to the lunar surface, exploring the South Polar region. So the exact landing sites haven't yet been selected. This is a montage of some of the proposed landing sites, all clustered around the South Pole. Now, what's so special about the South Pole? Why are we exploring this particular region of the moon? Well, a certain aspect of the moon's orbit. See, the moon's orbit is such that its spin axis is about a 90-degree angle to its rotation plane, or to its orbital plane. And because of that, unlike the Earth, where our poles go from 24-hour sunlight in the summer to 24-hour darkness in the winter, for the moon, the sun it's always dark, permanently shadowed. That's what I get for putting permanently shadowed in my title. Okay. Unlike the Earth, at the lunar poles, the sun is always right on the horizon. But what that means is if you go down into a depression, into any of the many craters that are ubiquitous in the South Polar region, the moon can never rise above the horizon. They're permanently shadowed, always in darkness, and that makes them incredibly cold, just a few degrees above absolute zero. Now, because they're so cold, any water ice that gets into those depressions stays there and is stable. So this is a map of ice in the lunar South Polar region from what we call a neutron spectrometer. And this is showing that water ice could be ubiquitous in this region, particularly in these permanently shadowed regions. And this is one of the primary goals of Artemis, is to explore this. Now, we understand this here in southern Arizona better than anyone because water ice is, of course, the first ingredient in EGs. And if you're going to establish a permanent or long-term presence on the moon, you're going to need some refreshment. So big motivation for Artemis is water ice. For me personally, I like EGs as much as the next guy, but the water ice isn't what excites me about Artemis. What excites me about Artemis is how different these landing sites are from these. These are 2 of the Apollo landing sites. And the Apollo missions to the moon in the last century mostly landed in relatively young, smooth volcanic terrains, whereas Artemis, all these landing sites are in extremely rugged, extremely heavily cratered, and extremely ancient sites. So Artemis is going to explore some of the oldest surfaces on the moon, unlike what we saw with Apollo. And on top of that, as you'll see, Artemis is actually going to land on the rim of the largest and most ancient impact basin on the moon. So Artemis is really taking us back to the early days of the moon to let us better understand early lunar evolution, which is a topic that I'm really interested in. But why? Why should we care about early lunar history? Now, it was long ago and far away, so who really cares anyway? To try to convince you of why we should care about early planetary evolution, I'm going to make an analogy, and this is probably a dangerous thing, but let's talk about psychology. So it's a dangerous thing to talk about something about which I know nothing about. This might seem to be an even worse idea if, for example, my wife were a professor of psychology at the university, but she's not here. So let's talk about psychology. Think about, the proverbial trip to your psychologist or therapist. You lay down in the couch and you just start to vent. You spill your guts. Oh, doc, work is really getting me down. My boss is just driving me crazy. Not you, Mark, different boss. But what does the psychologist do? They sit back in their chair, they look thoughtful for a moment, and they say, let's talk about your childhood. Tell me about your mother. And you're thinking, what? I'm talking about work here. I don't want to talk about my mother. But psychology understands that our earliest experiences are really formative for us as humans. Going back to Sigmund Freud, we've understood that the earliest evolution of our lives as humans, our earliest memories, earliest experiences as children, continue to affect us throughout our adult lives. We're carrying around this baggage, and it affects everything that happens subsequently. And so if the moon were to walk into the psychologist's office and lay down on the proverbial couch and start to vent, oh, doc, I don't know, it's just plagioclase, except for the mare, don't get me started. What's the psychologist going to do? He's going to sit back, look thoughtful, and say, oh, Luna, very interesting, but tell me about your childhood. Tell me about your mothers. You had two of them, right? Tara and Thea. What about your childhood? I hear it was really heated, because our planetary psychologist here understands that planets are like people. They're really complicated. They carry around the baggage from their birth and their early years throughout their evolution. If you want to understand the moon today, you need to go back to its earliest history. And so, why should you care about early lunar history? Well, a couple of reasons. One, as I've been saying, the early history of the moon sets the stage for everything that came after. You can't understand what the moon is today without understanding where it came from and those early periods in the earliest history of the solar system. Two, the moon actually bears one of the best records of the early history of the solar system as a whole. The history of impacts and bombardment, the formation of the planets, is recorded really well in the surface of the moon. And so by studying the early evolution of the moon, we're learning about the early evolution of the solar system. And third, and perhaps most salient for us as humans, is that the birth of the moon is tied to the birth of the Earth. It's one and the same event. We can't understand the Earth if we don't also understand the moon. And so, with that as motivation, let's go and talk about the early history of the moon. So, the origin of the moon. It's been widely understood for a long time that the moon formed in some manner of giant impact. I'm showing a hydrocode simulation here from Robin Knupp. Eric Asfog here at LPL was heavily involved in this work. And this came to be the agreed upon view of the formation of the moon. Roughly 20 years ago, as a field, we reached a consensus that the moon formed in a giant impact like this. You can see little moonlets forming, but they break up. This doesn't actually get you all the way to the moon. A giant impact that blasts this material out into orbit around the proto-Earth, and eventually this material orbiting the Earth coalesces to make the moon. This became so well accepted, it became called the canonical moon-forming impact. Anytime something gets accepted into the canon, you know you're in trouble. Once it's holy and unquestionable, that's when people really go at it. But about 20 years ago, this was the state of things. A Mars-sized object struck the forming Earth at a roughly 45-degree angle, and the ejecta coalesced around the Earth to make the moon. Now, the moon is really important to us on Earth, and it's really important to us as humans. This moon-forming impact completely changed the Earth. As humans, we have a real deep connection to the moon in a lot of ways. The moon, it's romantic, it inspires poets, it inspires artists, but it's also the moon forming event is what made the Earth. The Earth wouldn't be the planet that it is without the moon. The moon forming impact changed the makeup and size of the Earth, changed the abundance of volatiles and things like water relative to what they were before. And more than that, life on Earth really wouldn't be possible if we didn't have the moon today. The moon actually stabilizes the angle of our spin axis so that we're relatively constant in time, which stabilizes our climate. This is unlike Mars, which doesn't have a moon, and its spin axis is just wobbling up and down like a top, making its climate wildly unstable. Complex life couldn't have evolved on the Earth without the moon. So next time your love is waxing poetic about the moon and saying, oh, the moon just looks so beautiful tonight, you can respond, yeah, we'd all be dead without it. Because nothing says romance like reminding someone of their own mortality in the grand cosmic scheme of things. But it's true. We're here because of the moon. The other key aspect about the moon's formation is that it formed really fast. Now, planet formation, you're typically talking million year, 10 million year timescales. But this disk of material around the Earth would have coalesced to form the moon much faster than that. Within 1 year, you've already formed a large fraction of the moon. And this rapid formation of the moon is really key because as a result of that, the moon formed really hot. All of the energy of all the impacts of the material colliding together to create the moon doesn't have time to dissipate, doesn't have time to radiate away. So the moon formed incredibly hot and even molten. The moon may have been molten all the way to its core, or there may have been a shallower layer of magma. But regardless, we know that the moon had what we call a magma ocean, and that sets the stage for its subsequent evolution. So the moon had a magma ocean, and this magma ocean then started to cool. As it started to cool, it started to crystallize. And this is something that people have been studying for decades. Ananya Malik in the Geosciences Department is doing experiments on magma ocean crystallization right now. But the early studies of magma ocean crystallization recognize something really fundamental. As this magma ocean starts to crystallize, first you start forming really dense minerals, minerals that are more dense than the magma, and they sink. Things like olivine and pyroxene building up the lunar mantle. About 80% of the way through that crystallization, something changes, and you start making a new mineral called plagioclase. Plagioclase is really buoyant, it's light, it floats. So that plagioclase floats up to the surface and starts forming the lunar crust. And this continues until the mantle grows, the crust thickens, and you have a solid moon. This is a really important prediction because one thing that the Apollo astronauts brought back was samples of the plagioclase-rich lunar crust. This is a rock that's been called the Genesis rock, one of the older, but certainly not the oldest samples of the lunar highlands, and it is a very plagioclase-rich rock, which gives us very strong evidence for this idea of a lunar magma ocean. This plagioclase is also why the face of the moon is so bright. Full moon tonight, when you look out, you'll see much of the face of the moon is incredibly bright because it's this highly reflective mineral here. So the crystallization of the magma ocean gives us the bright plagioclase-rich crust that we see, but it also gives us something else. It gives us something that we call creep. And for Halloween, this is very appropriate. We talk a lot about the creepiness of the moon. CREEP is an acronym for potassium, rare earth elements, and phosphorus. It includes a lot of elements, including the element thorium. And this is a global thorium map. This is the near side of the moon here. And what we see is that there are areas of the moon that are incredibly enriched in thorium, much higher than you would typically see on the Earth. And the reason for this is because of the magma ocean. As the magma ocean was crystallizing, there's some elements that just don't want to go into the crystals. We call them incompatible elements. They keep getting more and more concentrated in the melt. Those elements are creep, including thorium, and that's what's responsible for these high concentrations of uranium, thorium, potassium, particularly in this near side region. To help people understand this, an analogy I like to use a lot is putting a soda can in the freezer. If you ever, you've got this warm 6-pack of Pepsi, you want one cold for dinner, you put your can of soda in the freezer, thinking, I'll come back in 5 minutes. And how often do you not come back in 5 minutes? I mean, I personally never forget, of course, but I hear some people do. What happens when a can of soda freezes? The water freezes first, and the high fructose corn syrup becomes progressively concentrated in the liquid. Well, creep is simply the high fructose corn syrup of the moon. It's becoming more concentrated in the late stage liquids. And so continued crystallization of this magma ocean, you get this thick, solid mantle of olivine and pyroxene, this thickening plagioclase-rich crust, and this layer of creepy magma ocean liquids sandwiched between the two. Another thing that these models predict is there's one other element that doesn't like to be in these early crystals, and that's titanium. It's not until very late in the process that the latest formed mantle minerals become very titanium rich. And titanium is heavy stuff. So these titanium rich minerals are very dense. So you make this layer of very dense material at the top of your forming mantle beneath the creep, beneath our plagioclase crust. Now, geologists call this near side region that's highly enriched in creep and thorium and these incompatible elements the Procellarum creep terrain. It's named after Oceanus Procellarum, which is a mare volcanic region over in this part of the moon here. And this played a very important role in lunar evolution. So in terms of our early history of the moon, we've now at least solidified it. We've got a solid moon in orbit around the Earth. The next thing that happens is it gets bombarded by impacts. And this is actually something that was first appreciated by a young grad student here at LPL in the 1960s named Bill Hartman. What he recognized was that if you take all the impact craters on the Earth, of which there's not a lot, and you take the rate of impacts on the Earth, which is fairly low. Here in Arizona, we think of craters as common. You just drive up the road and there's meteor crater. It's actually pretty special. There's not a lot of meteor craters out there. If you take the impact rate on the Earth and apply it to the lunar maria, these are these dark volcanic plains covering much of the near side of the moon. This is the man on the moon, or the face on the moon, the rabbit on the moon in China, whatever you see in the moon. This looks very young, very few craters. On the moon, young turns out to be about 3.5 billion years old. If you take the rate of impacts on the Earth and apply it to the lunar maria, it turns out they're really quite old. But if the lunar maria are 3.5 billion years old, the lunar highlands can't be older than the moon itself, or about 4.5 billion years. How do you form all of these craters in that short period of time? What Bill Hartman recognized was you can do this if the flux of impacts was much greater in early solar system history. And that's what we think indeed happened. So after the moon solidified, it was just completely bombarded and pummeled by asteroids. I mean, talk about a rough childhood here, from melting to being bombarded by asteroids. So this is where we're at. This is what we think we understand about the evolution of the moon. It formed in a giant impact, had these tumultuous early years in a magma ocean, and then was bombarded by impacts. This would be a perfect place to end this talk. We could all go home and we'd all be a lot smarter because of it. But this isn't really what interests me. I'm not as interested in what we know about the moon so much as what we don't know about the moon. It's the holes in this picture that interest me the most. I was reminded recently of a quote from the Republican presidential primaries. I won't mention any names, but one candidate turned and said to the other, "Every time you speak, I'm dumber for it." That's actually my goal here. My goal is for you all to leave here with more questions than you came. I want you to leave dumber than you started. I want you to have big questions in your understanding of the moon, because that's a great place to be here at the eve of the next wave of lunar exploration. We don't want to go to the moon to confirm what we know. We want to go back to the moon to answer these big questions. And so these are what you should be thinking about as you see, in hopefully a few short years, these images of astronauts walking on the surface of the moon again. Okay, so back to our analogy of our planetary psychologist. The moon tells this nice, short, sweet, simple story of its childhood. And what does the psychologist say? Well, that's interesting, but let's dig a little bit deeper. Let's start with your birth. Giant impact, you say? Well, the giant impact theory for the origin of the moon, like I said, 20 years ago, it was great, and everybody agreed. And then people started poking holes. There was some evidence that the canonical, the universally accepted moon-forming impact theory couldn't explain. And then some of the logic to justify why that model had to be also didn't hold up so well. And this basically opened the field wide up to new models. And there's a whole host of new models proposed for moon-forming impacts. I won't delve into the details of the problems and weaknesses and this and that, but people start proposing new moon-forming impacts. One view was a more symmetric impact. Instead of a Mars-sized object hitting an Earth-sized proto-Earth, you have a crash between equals, two roughly half Earth-sized objects colliding. And again, all this ejecta, it goes out into orbit and forms the moon. And this can explain a lot of the basic properties of the moon. Or maybe proto-Earth was spinning super fast, much faster than it is today, which is not at all unlikely, and it was hit by a smaller, faster moving asteroid or planetesimal, which launched material out into space, which coalesced in orbit to form the moon, which can also explain a lot of the basic properties of the moon. Or maybe it wasn't actually one impact at all. Maybe it was multiple impacts. Maybe it was a series of large-ish impacts, each of which launched material out into space that coalesced to form the moon, which again can explain a lot of the basic properties of the moon. And so we're left with the fact that the giant impact that formed the moon, the single most important event in the history of the Earth, we're still debating the most fundamental details and aspects of. This is still a big question in lunar science. How did the moon actually come to be? And that's something that hopefully we'll get some clarity on sometime. Okay, so the giant impact, there's some problems there. That magma ocean story, though, that seemed pretty solid. We like that. Magma ocean crystallized, you get the plagioclase crust, it explains the creep, everything's good. And that would be great if the moon looked like this. If the moon was a uniform sphere, then our crystallization of a spherically symmetric magma ocean would nicely produce what we have. Instead, we've got a moon that looks like this. So in topography, the far side highlands are really high elevation. The near side crust is really low elevation. If you use that to model what the thickness of the crust looks like, the crust is extremely thick on the far side and very thin on the far side, on the near side. This is the crust that formed out of the magma ocean. Why would magma ocean crystallization make such a strongly asymmetric crust? This is the most fundamental aspect of basically the physical nature of the moon today. This is one of its defining characteristics, this lunar asymmetry that affects many aspects of the moon. And we fundamentally don't know why. I wrote a review paper on the structure and evolution of the moon recently, and this is one of the things that I was calling out as one of the biggest unanswered questions in lunar science. Why is the moon lopsided? And if we look at the shape of the moon in detail, we've got the far side highlands, the near side lowlands as one of the key defining aspects of the moon. When we look at composition, another key player that I'm going to talk about in terms of asymmetries we need to explain is that the moon is not only structurally asymmetric, it's compositionally asymmetric. That creep material, those dregs of the magma ocean, the high fructose corn syrup of the moon, is all concentrated in the lunar near side. Again, why would this be an outcome of the evolution of the lunar magma ocean? And also, another key player that we're going to have to talk about in the early evolution of the moon is this feature right here. This blue region, this low elevation area here, is a giant impact basin. That much we know. It's an impact basin named the South Pole Aiken Impact Basin, incidentally also discovered by Bill Hartman here at the University of Arizona. But this is the oldest and largest impact basin, and Artemis astronauts are going to be landing on the rim of the South Pole Aiken Basin, formed very early in the history of the moon, and plays an important role in lunar evolution. So these are the dominant features of the moon in its early history. These are the things we're going to want to understand in understanding the moon's childhood. So first, why is the moon's crust lopsided? Why do we have far side highlands, near side lowlands, thick crust on the far side, thin crust on the near side? This has been a problem for half a century now, and a number of models have been proposed to try to explain this. Some of these models involve different forms of giant impacts. In one model, an impact on the near side excavates the crust, leaving the crust thin and the topography low. In another model, and Eric Asfog, I mentioned before in our department, was involved in this model, a real low velocity impact on the far side actually adds material to the far side to thicken the far side highlands. There's other models that involve asymmetries in the magma ocean, weird convection patterns, models invoking floating rock bergs or earth shine warming up the near side of the moon, but it remains an unanswered question. This is a problem that I've scratched my head about for a very long time, I think about 2 decades now, which is a little embarrassing, but something I noticed recently that I think is one possible explanation here is a curious outcome of some of these models of magma ocean crystallization. Because as that magma ocean is solidifying, it's evolving, it's changing. And in one model of magma ocean crystallization, if you look at the density of that liquid, in the late stages, as that plagioclase crust is forming, the remaining magma becomes really, really dense. It actually becomes more dense than the moon itself. And that's a weird situation to have this layer of overdense magma sitting on top of an underdense lunar interior. And that's actually a really unstable situation. You don't want your dense material on top. This is what you want. This would be a happy, stable moon. You've got a low density exterior with a higher density interior. And this is stable. You give this interior a little nudge, and it's going to stay put. It's not going anywhere because it's gravitationally stable. But this is not what at least this particular model of magma ocean crystallization gives us. In this case, an unstable magma ocean, if you've got a dense exterior on top of a less dense interior, if everything's weak, if everything's fluid and can deform really easily, the slightest nudge to this and the whole system will overturn really quickly. And your dense material will go to the center, your less dense material will go outside, and this is stable. But there's another possibility here, which is relevant to the lunar magma ocean, because if this interior is solid, it doesn't deform very easily, but your exterior is liquid, it flows really readily. What happens in this case? The dense material here can't easily sink into the interior. What happens is actually, it's a little unintuitive, but it's actually very simple. Picture this. Take a beach ball, and this is something my daughters love to do. You go into the pool and you try to push a beach ball under the surface of the water. This person was a little more successful than my 9-year-old daughter. If you actually can push the beach ball under the water, what's it going to do? It's going to try to float. It's going to try to pop back up to the surface or well above the surface if you're really good at it. The same thing happens for the moon. This is our beach ball. It's underdense and it wants to float up. It's at the center of the moon. Which direction is up? Up is any direction you want it to be. But this is, the interior is going to float in one direction, while all the magma sloshes to the other direction. And this is a gravitationally stable configuration. This is actually how the moon wants to be. This giant slosh of the remaining magma ocean into one hemisphere. Well, what does this do? Well, it turns out this would happen partway through crust formation. So you form a little bit of crust, a nice spherically symmetric uniform crust, and then all of your magma ocean sloshes to one hemisphere and continues to crystallize. What will it do? It will thicken the crust in that far side hemisphere and give us the asymmetry in crustal thickness we see today. I like this model. It's a really simple model. If that magma ocean model is correct, and this is a model from Lindy Elkins-Tanton up at ASU, so we'll blame ASU if this is wrong. If this model of magma ocean crystallization is correct, this sort of asymmetry is an inevitable result. But that depends a lot on the details of magma ocean crystallization, of which there's a lot of ongoing work on, and this is not necessarily a foregone conclusion. So we have yet another possible explanation for the lunar asymmetry here. All right, so the crust is lopsided. Volcanism is also lopsided. On this map of the moon, the near side is over here, the far side is in the center, so the near side is kind of straddling the edges of the map of the moon. What you see, though, is that the volcanic terrains, these dark volcanic plains that we see when we look up at the moon at night, are almost all on the near side of the moon. This was actually discovered by the Soviet Lunar program. They took the first pictures of the far side of the moon and realized, where's all the mare? In fact, the one of the few major mare regions on the far side of the moon is Mare Moscoviense, because NASA didn't discover it. But why all this volcanism on the near side? It's actually something my postdoc, Adrian Broquette, my former postdoc, now at DLR in Germany, was looking at. And he used geophysical models to look at not only where we see mare on the surface, but how thick it is. Created a really accurate model of the thickness of the mare, and then started looking for the lava you can't see, the lava that's underneath the ground, because maybe on the far side is all hidden in what we call intrusions in volcanism that never erupted to the surface. He added all of that up, and what he found is that there's about 3 times more volcanism on the near side than on the far side. Okay, why this volcanic asymmetry? This one turns out to be relatively easy to understand going back to creep. Again, it all goes back to the moon's childhood. Thorium is a heat-producing element. Other elements in creep, these other incompatible elements include uranium and potassium, which are our other two main heat-producing elements. All of the elements that produce heat on the moon are concentrated on the near side. That makes the near side warmer. That makes more melt. That makes more volcanism. So we can understand the volcanic asymmetry as a consequence of a compositional asymmetry. So the high concentrations of creep in the procellarum creep train are responsible for the Maria that we see, for why the man on the moon is here. Problem is, we just answered a question with a question effectively, because why then is the moon compositionally asymmetric? Why is the composition lopsided? Why do we have a procellarum creep terrain here? We saw the volcanism is concentrated on the near side. I talked about titanium rich, the dense minerals in the uppermost mantle. Well, titanium is also strongly concentrated on the near side, and thorium and creep is strongly concentrated on the near side. Why? Why would this be an outcome of an initially symmetric spherical moon? Well, let's look at the titanium first. So if you remember when I talked about magma ocean crystallization, we had this sequence. You're forming olivine and pyroxene, which sink to form the mantle. You're forming plagioclase, which forms the crust. The latest solids forming the mantle are really rich in titanium, a mineral called ilmenite, but just this dense titanium-rich material. And then the creep sandwiched between that and the crust. So you have this layer of very dense, solid mantle material that somehow all ends up on the lunar near side. How could that be? Well, a number of models have been proposed to explain it. The one I'm going to talk about is one that I was involved in recently, and it relates back to this impact basin I mentioned. So the South Pole Aitken Basin on the far side of the moon near the South Polar region. Remember, again, Artemis astronauts are landing very close to the South Pole there. It is the oldest and largest impact basin. It formed very early in lunar history. A big question is, how early did it form? And it plays a key role in lunar evolution. Well, a couple of years ago, a pair of studies proposed that South Pole Aitken is what caused all the titanium to be concentrated on the near side. So one of the studies was led by Matt Jones. He was actually the graduate student of my former postdoc, Alex Evans. So this work actually was born here at LPL when Alex was working here. But in this work, basically what we proposed was that the South Pole Aitken impact, this giant impact of an asteroid colliding with the south polar region of the moon, it put a lot of heat in. It made this big warm patch of lunar mantle. Warm stuff is typically less dense, it wants to rise. So this warm patch of mantle rose and then spread laterally, and as it spread laterally, it started bulldozing the upper mantle towards the near side. It pushed that titanium creep-rich material, which is these dark colors here, over towards the near side. Now, this sequence of simulations is actually from another paper that came out at the same time arguing the same thing, led by Nan Zhang. And both of these, I think, provide reasonable ways of getting titanium to the near side. Problem is, how do you prove it? Where is the evidence? There are other models that can also bring titanium to the near side. Well, I thought this was nice, and I was a co-author on it, so of course I had to think it was nice. But then when I looked at the paper by Nan Zhang, I noticed something. In his models, as all the titanium-rich material goes to the near side, then it sinks into the interior. But it does it in a very unique pattern. It goes in these almost sheet-like waterfalls of dense material cascading into the interior. But that left, at the end of his simulations, these strips, these narrow lines of titanium-rich material just below the crust that was stable, that stayed there. And there were these linear patterns in this intersecting polygonal pattern. And when I looked at that, it immediately rang a bell, because I'd spent a lot of time looking at the lunar gravity field. And on the near side, in the lunar gravity field, we saw this really bizarre polygonal pattern of linear gravity anomalies indicating dense material below the surface. And Nan didn't even mention this pattern in his paper, but the connection to me was clear. So I had my graduate student, Weigang Lang, work on this project. And Weigang looked at the gravity field and basically used the gravity field to model the distribution of titanium that would correspond to that. He took Nan Zhang's models to model what the gravity field from his models would look like. And it turned out everything agreed. So this sinking of titanium-rich material into the lunar interior, it's one of these big events in lunar evolution. It's been hypothesized for a long time, now we actually see some real concrete physical evidence for the nature of how this happened. So kind of shedding some new light into the evolution of the lunar interior. Okay, but let's go back to the South Pole Aitken Basin. We've got a little more we want to talk about in terms of early lunar evolution. And the South Pole Aitken Basin was really key. So the impact, as we said, it may have actually caused the migration of titanium to the near side. But what else can SPA tell us about early lunar evolution? Well, one thing SPA would have done is it would have excavated material from inside the moon and spread it out across the surface. And that's something that we can look for. Now, an interesting point is that models have predicted that basically most people have assumed that SPA was on a northward trajectory, moving from south to north. And models predict that all of that ejecta from SPA would basically pile up north of the basin on the far side highlands. Artemis is landing down here in this model. So according to this work, you wouldn't actually expect to find any ejecta from the South Pole Aitken Basin at all, which is not great for Artemis. But what more can we say about this? So the big question is, will Artemis encounter South Pole Aitken ejecta? And if so, what will it tell us about early lunar evolution? Well, I looked at this from a very simple standpoint. I spent a lot of time looking at impact craters and impact basins. And one thing I've noticed is that the shape of craters and basins is really diagnostic. These sort of oblique angled impacts, they make elliptical craters and elliptical impact basins, but they're not perfectly elliptical. They tend to taper in the downrange direction. They get narrower. This is a crater called Orcus Patera on Mars. This is Schiller, I think, on the moon. This is the Hellas impact basin on Mars. And in each of these, the downrange direction is consistent with their tapering. So I picked two giant impact basins, Hellas on Mars and the Sputnik impact basin on Pluto, which looks remarkably like Hellas and South Pole Aitken, despite being on icy Pluto. And in both of them, when we do fits to the rim, whether in topography and gravity and crustal thickness models, Hellas tapers, this down here is to the east. Hellas tapers to the east, and all the geologic evidence of ejecta blocks and so on say the impact was going in that direction. Sputnik Basin tapers to the south, and all the geologic evidence tells us that the impact was in that direction. So these basins are confirming that basins taper, they get narrower in the downrange direction. And we look at South Pole Aitken. Well, South Pole Aitken is tapering to the south. It gets narrower to the south in the same way that Hellas and Sputnik were getting narrower. And this tells us pretty clearly that the impact that formed South Pole Aitken wasn't from south to north, it was actually from north to south. Now that's important from the standpoint of Artemis, because Artemis is down here. Artemis is at the downrange end of SPA. Artemis is actually at the best place to possibly sample the ejecta of this giant and ancient impact basin. And that's a good thing in my book. So what of this ejecta? This is a recent model of a South Pole Aitken Basin forming impact from Robert Citron. And compare that to a crustal thickness model around SPA. These models predict that this impact should have excavated all of the crust and deep down into the mantle, that we should be sampling the lunar interior very deeply and very far back in time with this impact. And that could be really telling about early lunar history. And so what do we actually see? If we look at the composition, this is in that same view that we had before, but this is a map of thorium tracking possibly these late magma ocean liquids. We see that the floor of the basin is enriched in thorium. We also see it's stronger here on the western side of the basin, and the western half of the ejecta blanket is really rich in thorium, but the eastern half isn't. And that's really odd, because that's really hard to reconcile with these impact models unless you're actually excavating different material here than you are there. If this is representing magma ocean liquids, it seems like we're only encountering them in half the basin. Now that turns out to make perfect sense from the standpoint of the evolution of the magma ocean. Here I've taken basically the crust of the moon and I reconstructed what the moon would have looked like at the time the impact occurred. I've removed South Pole Aitken and all the other impact basins as well. And what I can do with this is map out the thickness of the magma ocean. So in a really simple model, the crust of the moon is just floating in the magma ocean. It's like an iceberg floating in our ocean. It goes down further where it's thicker, where it's thinner, it comes up higher. And what that means is that your magma ocean trapped between the mantle and the crust, the magma ocean is thicker where the crust is thinner. And the magma ocean is thinner where the crust is thicker. And eventually, as the crust is thickening, eventually you go from a globally continuous magma ocean, but that's variable in thickness and thicker on the far side, or thicker on the near side, thinner on the far side, to eventually it pinches out to zero thickness. The crust grounds, it basically lands on the mantle, and that zone spreads, and you basically squeeze the magma ocean to the near side, just like squeezing toothpaste out of a tube. And this would be a fairly simple outcome of the formation of the lunar crust as we see it today. But when we look at this, there's one point in time when the magma ocean is not quite all the way solidified, at about 98% solidified, where you only have magma ocean on the southwestern part of the impact basin here, which is where we see the thorium-rich ejecta. So this is giving us basically a snapshot of lunar history. At the moment of this impact, this would have been what the magma ocean looked like. We're catching the magma ocean in the act of crystallization at this intermediate stage, giving us a real nice constraint on where this fits in lunar history. And then progressing further forward, once you get to 99.9% crystallization, we're down to like the pure high fructose corn syrup in our freezing bottle of Pepsi. That's where these residual liquids are concentrated almost exclusively in this creep train where we see all the highest concentrations of thorium today. And now we can take this, we've got two different constraints in different points in space and time. South Polacan excavating sort of a weakly enriched earlier magma ocean, and the Imbrium Basin is exposing a lot of this creep-rich material here much later in time. We have two different concentrations, lower concentrations here earlier, higher concentrations here later, and we compare them to predictions of magma ocean crystallization, and it all matches and lines up nicely. So we've got two snapshots of the evolution of the lunar magma ocean on its way to crystallizing. Now, Apollo was sampling this stuff. Artemis will have the opportunity to sample this stuff, and in so doing, shed light on the evolution of the early lunar magma ocean. Now, how are we going to find this stuff? The moon's a big place, and we've got little astronauts. They're going looking for this unique material, for ancient magma ocean samples, or samples of the lunar mantle. How can we guide them in finding this material? Well, again, this impact should have excavated really deeply, not just into that thin magma ocean layer, but into the solid mantle underneath. Mantle is pretty dense stuff. It's got a much higher density than the crust of the moon, and that should have a signature that we can see geophysically. So my student Gabe Gallman here has been looking at that. He's been looking at the gravity field of the moon. When you measure these subtle, sensitive variations in the gravity field of the moon, you're basically sensitive to these subtle variations in density below the surface. He sees areas where the gravity field is just a little bit stronger, and those would correspond to areas where the subsurface is a little bit denser. When he looks at the gravity field of the South Polacan Basin, what he sees is that the rim region is incredibly variable, much more variable than the rest of the moon. This is actually one of the most heterogeneous areas on the moon because it has this ejecta, this mixture of mantle and crust that's pervasive in here. And so Gabe now can go through and take these candidate landing sites for Artemis and actually map them relative to the distribution of lunar mantle. And we can see where are the best places to sample early lunar mantle material using this data. That's something that Gabe is working on right here. So one last topic I'll address in terms of early lunar evolution goes back to that observation that Bill Hartmann had of the high flux of impacts very early in lunar history. Turns out there's a bit of a raging controversy there in the field over exactly what the evolution of impacts was. There are two very, very different views of the early bombardment history of the solar system. In one, the rate of impacts is just steadily declining with time. And that's represented by this gray line here, where 4.5 billion years is the age of the moon, 3.5 billion years about when the Mare are forming. In another view, early on, the rate of impacts was dropping really rapidly, and then somewhere around 4.1 to 3.9 billion years ago, there's a spike in impacts, and then it decays again. And this goes back to long debates over different samples from different basins, the ages of impact basins on the near side, the ages of craters and impact melt samples, and on and on. These two very divergent views of early solar system bombardment have very different implications for the evolution of the solar system as a whole. And it's gone back and forth on these. For a while, the declining bombardment was widely accepted. The late heavy bombardment then become really popular. Now the pendulum's swinging the other way, and the declining bombardment is becoming popular again. But this has a fundamental difference for not just the moon, but for the bombardment history of the Earth, the bombardment history of Mars, of everybody in the solar system. And this is a big area of disagreement. Well, this has different implications for the South Polacan Basin. So you can reconcile the South Polacan Basin with a declining bombardment if it formed relatively late, 4.4 billion years ago, 4.3 billion years ago. But in that case, there would have been about a dozen other South Polacan-sized basins on the moon that are hidden that we can't see today. Alternatively, if the South Polacan Basin turns out to be really old, more like 4.45 or 4.5 billion years old, well, in that case, it would support this late heavy bombardment, where the South Polacan was part of this spike, and the near side basins are part of this spike. But this all hinges on the age of this impact basin, which is something that Artemis, sampling the ejecta and possible mantle material ejected by SPA, will hopefully be able to answer. So hopefully, with this coming new wave of lunar exploration, we're going to be able to settle this debate. So where does this leave our understanding of the moon? Well, the moon is lopsided. This is its most basic fundamental property. It's lopsided in topography, crustal thickness, composition, and volcanism. These asymmetries date back to the earliest history of the moon, the first 100 million years or so of lunar evolution. But these asymmetries are fundamentally important for everything that happened, the subsequent 4.4 billion years, including all that volcanism that makes the man on the moon that we see at night. All of that relates to these asymmetries that are still very uncertain in their origin. The South Polacan Basin, this pivotal event in lunar history, may have a lot to do with that. And so landing on the rim of the South Polacan Basin, sampling this early material, is hopefully going to shed some light on this. Now, I'm a theorist. I like to sit back and think about big questions and make up models and write code. The answers to these questions are probably going to come from different people. So if you've been following our evening lecture series, our previous lecture by Jessica Barnes, she's going to be one of the people analyzing the samples brought back from the moon, looking at things like age and composition, and seeing what we actually learned by bringing back these rocks. A month from our next speaker, Angela Marusiak, she's going to be one of the ones putting seismometers on the moon that's going to be imaging below the surface, seeing the structure of the crust and mantle and what light that can shed on early lunar evolution. So lots to look forward to in lunar exploration, as well as in our evening lecture series. And that's probably a good point to wrap up here. So I'll stop and take any questions.
Thank you so much, Jeff. That was fascinating to hear so much of these ideas. For people that maybe aren't used to thinking about gravity and looking at gravity, maybe you can say like what percent, like if you're walking around the surface of the moon, how much would the gravity vary when you're thinking about these things?
A very, very tiny amount. So we measure gravity in milligals. So 1/1000th of a gal. A gal is 1 centimeter per second squared. Earth's gravity is about 10 meters per second squared. So about 10 to the minus fifth variation. But you get, variations of hundreds of milligals. So you're up to, 10 to the minus 3, 10 to the minus 2. Less than a percent variations. Something that amazes me is early terrestrial geophysicists could actually measure these subtle variations of the gravity field on the Earth with a plumb bob, a mass on the spring that would just be subtly deflected. I can't even envision doing that, but they did it quite well.
Interesting. Any questions from the audience here for Jeff? Yeah.
I guess like my question is, how exactly does that come into effect on like a large scale example, such as like the moon with Earth? That kind of seems.
So for the moon in the moon's orbit about the Earth.
Yeah.
Really good question, because the overall rotation and orbit of the moon potentially could have an effect. Now with the moon, as it's orbiting the Earth, it doesn't feel centrifugal force per se, because all of the forces balance in orbit. But very related to that, what it does feel is tidal forces. Like the moon raises a tide on the Earth and we see the ocean rise and fall. The Earth raises a tide on the moon. And so some ideas have tried to relate some of these asymmetries to the tides. A problem there is that that tide is actually symmetric. So it's much easier to make a bulge on the near side and on the far side than it is to make something on the far side explicitly. But that's one of the ideas that people have been looking at.
Do we have any online questions, Brian? Okay.
Jeff, in the early part of your lecture, you were talking about the most accepted theory of how the moon formed up until 20 years ago. It was the most accepted. And so I think I heard you correctly when you said when the impact event occurred and the projectile went out and began to form what became the moon. I thought I heard you say that process took about a year. Is that correct?
The process of forming much of the moon, the whole process takes a little bit longer. Basically, it comes down to the moon actually formed relatively close to the Earth, and its orbital time scale is pretty short. So like our moon takes a month to orbit the Earth now because it's out farther away. I don't actually know off the top of my head the orbital period, but it was much shorter when the moon formed, which basically caused everything to evolve much more quickly. So you're forming roughly half the moon in about a year in some of these simulations, which is incredibly rapid.
Yes.
Any other questions?
Yeah, Jeff, I was going to ask, how does your titanium sinking areas compare or contrast to subduction zones on Earth?
It's very interesting because in a way it's very similar, and ideas like that, where you start off with dense material below the crust sinking, triggering subduction, things like that have been proposed for Earth and have been proposed for Venus, in fact, as well. On the moon, that can't go that far because the one difference from the moon to Earth and Venus is the moon's crust is much lower in density. And so, whereas that exact same process would cause subduction on Earth or Venus, on the moon, that crust is so buoyant, it's going to stay up at the surface. But it's interesting because if the moon had a crust made of basalt, we probably actually would have had a period of plate tectonics on the moon associated with that.
So I'd heard that in the last month or two, they discovered a cave on the moon or a system of caves. And so I was just wondering, is that true? And then also, do you think that would have been formed by the magma ocean crystallizing or from an impact?
That I'll admit my ignorance. I didn't hear about that particular discovery. And I should be restating questions. Sorry about that. For our friends online, the question was about caves that have been discovered on the moon, and do those relate to the magma ocean? They have discovered a number of these caves, and basically what they're associated with, not so early as the magma ocean, because anything from then would have been destroyed by all the impacts that happened since. But from things like volcanism, if you go to Lava River Cave outside of Flagstaff, there are a lot of features like that on the moon that have been actually imaged from orbit, where you can see a collapse pit into one of these lava caves, as well as an impact ejecta. So a lot of these craters actually make a lot of melt, and they've discovered some cave-like features in the melt from these impact craters. I'm guessing the caves you're talking about are probably one of those two features.
I think it was like a lava tube.
Uh-huh.
Anybody else? Well, let's thanks Jeff again. Thanks so much.